to the first exoplanet seminar of 2024. Today, Niyati Desai is going to present. She's a fifth-year PhD student at CalTech with Dimitri Mawet, and she completed her master's at CalTech as well, and bachelor's in aerospace engineering and physics at MIT. And she's working on astronomical instrumentation for the detection of exoplanets. So,
thanks, Rosaire. Thanks for inviting me and hosting me on this visit. It's really nice to see Goddard. I've driven past Goddard many times because I grew up in New York and did a lot of trips down here, but never actually stopped to see it. So I'm really happy to be here. So as Rosaire said, I'm finishing up my PhD, and I just wanted to share a little bit about what I've been researching for the last 4 to 5 years, and what's on the horizon, and where I think we can go with some of the work that I've been trying to put out in this field. And so today I'm going to be speaking to you all about scalar vortex coronagraphs. I'm going to be doing an even split of experimental results and lab testing, as well as simulation and design work for future perspectives. And so before I get started, I know that this is an exoplanet seminar, so I'm going to just start with a little bit of overview and motivation, and if you already know this, that's great. But just to draw your attention to, again, the system that we're looking at here, and the parts of the system that my PhD work in particular addresses. So we're looking at high contrast imaging, particularly for the application of directly imaging exoplanets, and this is a simple ray trace diagram of an on-axis star and an off-axis planet here drawn in purple. And this path here is a pretty typical coronagraph setup for example, a vortex coronagraph. And so what I mean by that is here in the focal plane, where the first focal plane after the DM, we usually have our focal plane mask. And today I'm going to be talking to you explicitly only about vortex focal plane masks and all these different kinds of focal plane masks that involve vortex. And what that optic is designed to do is take the light that is focused at the center of the vortex, so any on-axis light, spread it outwards of a certain radius so that in the next pupil plane, you could put a LEO stop and block out any of that unwanted starlight, but let any off-axis source here drawn in purple through all the way, so you'd be able to image your planet. Okay, great. So we're pretty much all on the same page for the optical system that we're looking at. And of course, I didn't really talk about the DM here, but that's a really critical part of this system, and I'm going to spend a little chunk in the middle of my talk talking about different ways to control a DM and the best possible algorithms that might go hand in hand with different vortex chronograph masks, whether some are better suited or worse suited for the different applications of chronographic masks we're talking about today. So just to give you a little sneak preview about that. So for our purposes of chronography, the first thing that I'm really exploring that we need in order to reach these, high contrast targets is high-performing focal plane masks. And I mentioned I'm going to be talking about vortex chronographs, and today I'll be discussing 2 different flavors. So the first one you might have heard of more commonly, it's the vector vortex chronograph. And the idea is that when you have this vortex chronograph in your focal plane, the light that passes through it gets a phase ramp imprinted on it that looks like a spiral. And the key component of a vortex mask is that it's able to achieve this theoretically perfect starlight rejection within this LEO circular plane, region that you've designed, if the number of spiral phase wraps that you give the light after it passes through your optic is an even integer number. So what I mean by that is the light passes through your optic, and it can pick up a spiral phase that'll go from 0 to 2 pi, or 0 to 4 pi, or 0 to 6 pi. If it goes 0 to pi, it's not an even number of wraps. And so you need an even integer number of phase wraps. And that number is called the topological charge. So you might have heard of like charge 4 vortex or charge 6 vortex. What that means is you've got 6 times 2 pi wraps. You either go from 0 to 12 pi, or maybe you go 0 to 2 pi 6 times. Either way, you get this principle. And I'm happy to talk a little bit more about what the different charges mean, but for the purpose of today, all we need to understand is that I'm mostly doing a comparison of the same charge vortex across the different possible designs. I'm only looking at a charge 6 vortex. So now back to the slide here. So the vector vortex chronograph, that's one of the 2 flavors. And the key component here is that it works well in broadband light, but it's polarization sensitive. And that's because of the fundamental way it imparts a spiral phase ramp onto the light. You can see here on the right, there's a simple Jones matrix that explains what happens when you send light in different circular polarization states. So if you have only right circularly polarized light, you'd pick up one of these vertical columns, the e to the IL theta ramp. But if you send in left polarized, circular polarized light, you get e to the minus IL theta ramp. So these are still perfect spiral ramps for each of the two polarization states, but they're in opposite directions. Now, when you start to have issues of maybe it's not perfectly polarized light, or you're sending in light that's slightly off from the exact split of 50-50 polarization that you wanted, now you're sending in light that hits a DM that's in two different polarization states, and a deformable mirror might have difficulty correcting two different signed ramps at the same time. So that's why this is a pretty big issue for the vector vortex chronograph. Usually, when we use vector vortex, we filter out one of those polarization states. That's a big hit we're cutting out 50% of the light, or you have to split your entire optical path and have, one for each polarization state for the entire rest of your system. And so that's really the big issue we're talking about here. And the reason I'm highlighting that is because the other flavor of vortex chronograph is the scalar vortex chronograph, and that's what the rest of my talk will focus on. And that one, it doesn't have any sensitivity to polarization, so it doesn't care if you send in totally unpolarized light, it's still able to put that spiral pattern into the phase, but it's extremely chromatic. And that's because it simply takes a piece of glass, let's say, and varies the thickness to have that phase ramp pattern on it. So that means you're getting a scalar pattern. It's not dependent on the polarization state at all, but when you send in a slightly different wavelength from the wavelength that it's designed for, that specific thickness that you've mapped out, now you don't get a perfect number of integer phase wraps. You might get 6.1 phase wraps or 5.9 phase wraps, and then you don't get perfect solid rejection. So the equation here just shows that you have a very clear wavelength dependence, and as soon as you start to move away from the wavelength you care about, you start to have problems. So that's the first half, is that chronographic instruments definitely are going to require high-performing focal plane masks. We've got two different flavors of vortex ones. But of course, the second half is being able to do precise wavefront control, wavefront sensing and control to control your EDM to make those focal plane masks perform as best as they possibly can. You want to be able to send in the best possible wavefront, correct as much as you can beforehand for that vortex to be able to do its job the best. And so on the right-hand side here, you see an example of, this is actually done in lab at JPL on the in-air chronograph testbed, a dark hole being dug, that's what we call it, when you're trying to remove any of that stray light in a particular region of interest where you would be looking for exoplanets. So I'll talk a little bit more about that later, but this is the main idea. These are the two components I'm going to be talking about today. So honing in on the scalar vortex chronograph, if the limitation is that you've got a lot of chromatic behavior, let's see if we can sort of address that. So these are some of the goals. We're all pretty familiar with some of these requirements, hopefully, that have been set not just by like mission ideas like HW or anything, but actually by the science, by the targets that we're trying to look for. And so all of these are really important, that you want to be able to achieve this really high level of 10 to the minus 10 magic number contrast, but also across this bandwidth. And that's a key one for this particular application because it's very chromatic. You want to have a small inner working angle that comes in with the choice of charge. So if you're going to choose a smaller charge vortex, you might have a better inner working angle, but you have a trade-off, which is in the third bullet, which is sensitivity to low order aberrations. So you really want to make sure you're nailing all of these at once. You can't just pick and choose one or two. You really take a big hit on the others. And the last one is high throughput, because at the end of the day, we're trying to get spectra of these planets. So taking this goal and broken it down into 3 different research questions. The first thing is, okay, we're looking at these scalar vortex chronographs. We're saying that they're chromatic. How chromatic are they? Let's see what we're dealing with here and then address how to move forward from there. So the first thing we want to do is experimentally characterize the simplest possible design that we could think of for one of these, and then see where we have room to grow and improve. So these are some of the test beds. The high contrast spectroscopy test bed, HCST at CalTech, shown on the top, and on the bottom is the in-air chronograph test bed, IACT at JPL. These both have this particular scalar vortex chronograph that's shown on the left installed on them currently. And this is a very simple charge 6 glass scalar vortex chronograph design. You can see the microscopic image there. And you can see these like pie slices, sort of sectors that are drawn in. This is a top-down view. And you can count that there's 6 of them, so that kind of makes sense. It's a charge 6 design. But you can also see that each of those 6 sectors has 6 smaller steps. And that's because it's one of the easier ways to manufacture this phase ramp is discretely. And so you're not actually getting a nice smooth ramp right now, but for the purposes of this early initial test, it's good enough for what we're trying to do. We want to see how chromatic is this type of thing first. And so we threw it on both of these test beds. and we did some broadband characterization. And so this plot here shows without any wavefront control first, how much starlight are you really rejecting for 685 nanometers to 820. So that's about 20% range that we're looking at, and for each of those wavelengths, we have a different curve. And if you look at the best performing one, so this is raw contrast versus angular separation, so the best performing one is the one that achieves the lowest contrast. It's the orange curve here with the triangles, and that lies right in the middle at 775 nanometers. And that's good because that's actually the wavelength that this mask was designed to perform best at. And this plot really shows the spread of how does performance degrade as you're stepping away farther and farther from that design wavelength. And so you can see here that the two ends, they go farther and farther away from the best possible performance. But again, this is without any wavefront control. So of course, the next step is to add wavefront control and compare it against our current option, which is the vector vortex chronograph, which has been, developed a lot more in the last decade, and then we've sort of debugged a lot of those issues already. And so here we have a direct comparison on the exact same test bed, the exact same size of dark hole, the exact same bandwidth. So we have narrow band on the left, broadband on the right, scalar vortex on the top versus vector vortex on the bottom. So it's a nice, easy comparison. And right away, you can easily see that in narrowband, we have pretty comparable performance. Still a little factor of 2 or 3 that's missing, but the test bed hasn't been optimized for this mask. So that's pretty reasonable, and I think that's an acceptable difference. But as soon as you jump to broadband, 10% even, not even 20, you immediately see a whole order of magnitude degrade when you're looking at this broadband performance. So right away, okay, we know the scalar vortex is too chromatic. We got to address this. We got to tackle that. What can we do? Yeah, of course. Yeah. Mm-hmm. Yeah, actually, I think this is 10% total. 685 to 820 is not 20%. Is that 775? Yeah, so this is actually the whole range, 685 to 820. It would be the average of the purple curve and then maybe the last red curve and the central curve would be, right? So, and also this is from 3 to 10. Oh yeah, the blue plus. Right. I don't have one. Oh yeah, you're right. Actually, I did that wrong. Right, 700 to 820. That is 15%. It's not 10. Yeah, and this is without wavefront control. So then when we added wavefront control, we were able to do way better with the vector vortex than we were with the scalar. So, but you're right. This doesn't look like that much spread here for without wavefront control. So maybe it was not seeming as chromatic here. But then when we added it, we were able to, the wavefront control algorithm that we were able to do, right, the dark hole digging process, was able to get a larger gain than it was for a scalar. Yeah. Yeah. This is on average like 10 to the minus 5 something for 3 to 10 if you were to take that. So I think that's really where it comes from. But you're right, this is actually 17 or something. Bandwidth. I thought I had misspoken earlier. Yeah. Yeah, so definitely for the vector vortex it is, and for scalar we took out the analyzer and polarizer, so it shouldn't have been single polarization light. Yeah, no worries. I can repeat the question. The question was if it's single polarization light. Yeah. Mm-hmm. So I'm not actually trying. I've read a couple of papers about the development that's been going on with trying to do DM control with multiple polarizations, and the solution seems to be really to split them and come up with different solutions. So if you're asking if it's possible to come up with a solution for both on one DM, it seems to me like it's not something that, yeah, you're physically trying to correct for speckles that are changing for two different sets of polarization states. So if you try to correct for one, you're getting the exact opposite correction for the other state. Yeah. Right, because at this stage, we're not really correcting for like turbulence and stuff like that with the DM. We're correcting for aberrations that are being created by our own optics. Yeah. Did someone else have a question also?
It's more of a comment, but on your next.
Mm-hmm. Because of.
The algorithm will tend to. That's obviously. Scalar Vortex.
I should compare single to single. You're saying. Yeah. Okay.
Probably why you have.
Yeah. Okay. That's a good point. Yeah, I'll have to also check that shouldn't be a really difficult thing to change in our setup. So. Yeah. Oh yeah, the statement was that you're taking a penalty by trying to do correction for dual polarization with the scalar vortex as a not direct comparison with the single polarization for the vector. So maybe it'd be better to do comparison of two single polarizations for the vector versus the scalar. You have to check to make sure that this is dual polarization, but I'm pretty sure it was because we took out the. But yeah, you're right. The ultimate goal is to have it be unpolarized light, so you don't have to take this hit. Yeah. Yeah.
Another, of course, difference
Mm-hmm.
is the dark hole.
Oh, like it's pretty brighter on the right-hand side. Yeah, this is an artifact of the test bench. So I think there's just something it's been that way for a while that just hasn't been addressed. But yeah. Oh yeah, I don't think it's particular to either of these because these results are more than a year old, and we've done later results, and it still shows up like this speckled pattern is not quite metrically uniformly distributed. No worries. Yeah, it's true. The field stop position does look slightly different here. And another thing to keep in mind is that these two vortexes have slightly different central wavelengths. So the entire image is scaled a little. So when you're so the vector vortex is like 635 and the scalar is 775. So we tried to have comparable bandwidths, although it's not the same wavelength. But yeah. Mm-hmm. I know it was pretty unobvious to me when I first was doing this. I was like, well, I can't show these two at the same time. But yeah. And I'll show a bunch of more dark holes later, so it's good to clarify all the questions now. Okay, yeah, so we did this, and when we saw what we saw. And one of the first questions to ask before trying to over-engineer the heck out of the scalar vortex and make it better in all the possible ways we could think of is to see if the wavefront control method that we were using is the best one suited for scalar vortex, even though we know it already performs quite well in the vector. And the main reason for that is because the method that we've been using is pairwise probing electric field conjugation is pretty standard for this type of application, but it definitely requires having a good model of every optical element in your system. And so if we're not having a very good model of our scalar vortex, maybe the clocking is slightly wrong, maybe we are modeling something that's not actually what we're getting, and we should be improving that, or how the light is interacting with it, especially with all these sector jumps and all these things like that. We should just see if that's our limiting factor. And so it's also a good excuse for me to learn all the different wavefront control methods that are out there, and they're growing every day. So just to be clear, this wavefront sensing and control here we're talking about is the dark hole digging. I already showed this, Jeff, but I'm just showing it again, is what we're sort of talking about, this process. And all these experiments were done at JPL. And so what I wanted to test was a nice comparison between the vector and the scalar, once again, but for 3 different wavefront sensing control algorithms. So here I wanted to stop and make a distinction, because I know a lot of people have heard of wavefront sensing and control algorithms. You might have your favorite flavor of algorithm, but I wanted to stop and make a distinction between the wavefront sensing and the control, because when you use these, sometimes you combine them all together and you just, plug and chug. But I really wanted to make this division because lately there's been a lot of new papers about new different algorithms, and there's a lot of similarity between them, and there's a lot of different names. It's easy to get confused. So I wanted to separate the wavefront sensing side and the control side, and then separate the model-based ones and the model-free ones. So on the left-hand side of this little quad chart that we have, it separates the model-based and model-free. Again, that means you have to have an optical model of your entire system and all your elements. So in the top left, you have pairwise probing as the wavefront sensing method that you're using. So you're using that to figure out how much light is left in the region that you want to remove. And that's model-based version of that is pairwise probing with EFC. That's the regular out-of-the-box one that we've all been using. Now, if you go below that, you still use pairwise probing to do your wavefront sensing, but now you remove the model. That one has been named IEFC, so it's implicit electric field conjugation. So it still uses pairwise probing to do the wavefront sensing. Now, on the right-hand side, if you change the wavefront sensing method and you don't use pairwise probes, which you totally can do with the self-coherent camera, I'll talk a little bit more about how that works, then that's a model-free method that's just called self-coherent camera in most papers, but here I'm going to call it self-coherent camera plus electric field conjugation because that's the process you're doing for the control. And then there might be some hybrid method of these that we haven't really looked into yet, which could be kind of interesting. So again, I'm separating these wavefront sensing and control because it starts to get confusing when you're looking at new algorithms. And some of this gets really, really into the details. I'm not going to read all of the things that I'm really showing here in case anyone's particularly interested in how each of these different steps works. But I wanted everybody to walk away with this idea that these are three different methods that all kind of operate on the same principle, which is that you do wavefront sensing. However you do it, in this case, you're using pairwise probes. At the end of that step, you get some estimate of the light that's left. So here you get an estimate of your ES, or your electric field, left in the region of interest. And this equation just shows that you're trying to minimize that thing. So as I go to the next methods, we're always trying to minimize something, and those things are pretty much proportional to each other. So in this method, you get your electric field estimate, and then you try to minimize it, and that's through the control step. And now in order to do the control, you need to know how to control your Jacobian, to control your DM, and so you need to build the Jacobian. We do that here by poking each actuator on the DM, but since we have a model of the system, we can do that really quickly because we have a model of what happens. So you just poke each probe on your DM in simulation. You're really fast to get a Jacobian. It's really fast to start doing the control steps because you've got your estimate. And you iteratively go through getting your estimate, poking the DM, getting your estimate, poking the DM, minimizing that electric field. Pretty simple for the method that we've been doing and the terminology. I think it's going to get only more confusing from here. So now you do self-coherent camera. Now you get rid of your normal probing that you're using to do wavefront sensing. Now self-coherent camera, if you're not familiar with it, you have the same optical setup here on the top, and in the Leo plane, normally where you're blocking out all of that light that your focal plane mask, let's say your vortex is scattering, here you introduce a new pinhole right where that light was landing. And so that reference channel is now re-allowing some of that light that you've just rejected back into your focal plane. And that light, importantly, is coherent with any of the bad light that's left over in your image channel. That's helping you to see, because it's interfering perfectly with that light, and you get fringes, how much light is left over, what do we really need to remove? So that's the main operating principle. On the bottom, you can see an image of your source, and then a source with a companion, and then a source with a companion with that pinhole open. So you see filters, you see fringes all across your light, except not across your companion. And so you can easily see what that starlight is left in your image. So you use this process of taking the fringed image and then getting your estimate of your intensity in that leftover, in that focal plane of the whatever leftover light that is. And so that intensity here is what gets replaced in that equation. Before we had an estimate of electric field, now you've got your intensity, it's all proportional. Same thing, now you move on to the control step. Now you don't have a nice model of the system, so you have to build your Jacobian by hand. So now you need to poke your DM in your actual experimental setup, take the fringed image, figure out what that intensity is, poke the DM again, take another image. It takes a lot more images to build the Jacobian by hand. You have to do every single step. And then once you've built it, now you can minimize that light that's left over the exact same way. The last one is IFC. This one's a little bit more hard to separate between the wavefront sensing and the control steps because they're sort of intertwined. And the reason for that is because here we're looking at the change in intensity as you're modifying the DM. So you're not actually getting, at any point, a static estimate of the light that's left over. You're only looking at how that light is changing with each step. And so you're basically applying modes to your DM, taking the difference between these probed images, the probed DM. The DM is probed, you take your images, you take the difference between those images, and then you're able to minimize that difference iteratively to control how much light is left over. So these are the three different methods. It's okay if, you know, it's not that interesting to you how each one works, but now we get to the results, which is the cool part. To do a direct comparison, here I'm only showing broadband results. So it's the same setup. On the top row is the vector vortex, on the bottom is the scalar. These were all done on the same test bed. These were all done for the same bandwidth. Again, they had different central wavelengths, but the same bandwidth. And the scoring region here is all 5 to 10 Lambda-V. It's highlighted in that dashed white line. And so for broadband, you can pretty much immediately see that the scalar vortex still does worse than the vector. If you look at the IEFC and the SCC ones, it's much more obvious. But for the pairwise probing one, it's a little bit less obvious. And I think that that's just because we've been able to optimize the process a lot more for pairwise probing and EFC than the other two methods were newly introduced onto this test bed. And this was the work of a few months. So it really is pretty quick to see the difference, at least in broadband. I'm not showing the narrowband results here, but you can check out my SPA paper if you wanted to see that. It's more obvious that they're performing comparably when you look at narrowband. What I think is more interesting than just the dark holes, which is what people tend to look at, is actually the performance process. And so if you look at the convergence rates, this was the part I was not expecting to see, which is if you're looking at this plot, it's iteration on the x-axis. So that's iteration of correction within the control loop, and the y-axis is their mean normalized intensity or the contrast within that region of interest. Then, for sure, the scalar vortex lines are all like one order of magnitude above, so they're performing worse than the vector. But if you look at the convergence just within 0 to 10 iterations, how fast the model-free methods really get down to that darker contrast, and then sort of plateau much quicker compared to these other methods. And so you might look at that at first and think, okay, but is this really representative? Because you're looking at iterations here. So that's iterations of control steps. But if you look at in real time what that really translates to, it's important to look at these two plots side by side. The model-free methods take so much longer to build these Jacobians, take so many more images, and then as soon as they do have that idea of how to control their DM, it's pretty quick. Within a few iterations, they're able to get down to the same levels of that the model-based ones are. If you're comparing, not quite how deep regular EFC pairwise probing EFC gets. So this is one of my favorite plots just to see side by side, because it was a little bit unexpected to me to have learned this, and it's something to keep in mind when you're thinking about what type of wavefront control method is appropriate for your system or telescope or observatory. So now we've done this foray into wavefront control and comparing these. Let's go back to the main storyline, which is, okay, we tried to see if we were limited by the wavefront control algorithm that we were using, but at the end of the day, the scalar vortexes are just still too chromatic. So what can we do to change the designs of the scalar vortexes to make them better performing in broadband? So first thing to do is look at a couple of the simple patterns when you're just doing a regular charge 6 scalar vortex. So back to this discussion about charges, right? If you're looking at charge 6, you want to go from 0 to 2 pi 6 times, or from 0 to 6 times 2 pi. So the first one here is a classic vortex. That's what you would think of. You would go 0 to 12 pi. That's just one simple wrap, and you can see the profile cut in the left-hand side, and then the top view of the phase map on the right. And then the second one is the sawtooth, we call it, because of what the profile sort of looks like, and that's doing 6 times those 0 to 2 pi wraps. Now, intuitively, we didn't expect to see any kind of difference in whether we would choose one of those over the other, but spoiler, that we did find out that there is a difference, and that sort of only showed up when we came up with new ways to assess the performance of these, other than just looking at simple 2D wavefront propagation. So this right-hand plot shows when you propagate through your entire system these different designs, what happens. But that's kind of annoying and might not be the most telling way to see how well they might perform and which one you might choose, because yeah, you could also just build the whole thing and put it on your test bed and get your number and then decide. But this is one of the only metrics that we had starting out, and so It was nice to come up with new ways to compare these. And the last one here is the staircase one, as I had shown before. This is the one that we actually built and got those earlier results on because it was easier to manufacture when it's got these flat steps than a smooth ramp. That was purely for manufacturing purposes. But doing this propagation just to test, just to see what does it look like when you do 2D wavefront propagation, we see here pretty comparable performance as you increase the bandwidth. Doesn't look like there's that much of a change. But the idea is how can we assess new designs that are not going to be as simple as these? New crazy patterns that might have all kinds of weird shapes going out. And so this is the part that I think is really cool to think about, which is that any azimuthal design, that means that it doesn't have radial features, but if you were to sweep around azimuthally, you have the exact same pattern anywhere. Any azimuthal profile can be decomposed into other vortex charges. And we know how simple vortex charges work. So we already know how a simple charge 2 vortex operates. We know what its inner working angle is theorized to be. We know what its sensitivity to low order wavefront aberrations is. We're familiar with these things. So if we can take a complex design, sort of decompose it into charge 2 and charge 6 and this much of each of these different modes, then we can have some way of predicting the performance without doing necessarily all this 2D wavefront propagation, doing all the simulated wavefront, low order wavefront aberration sensitivities and all these things. Maybe we can even get some other insights. And so this math just explains that you can take any weird profile, break it down into a Fourier series, look at the different coefficients for each of these, know that each term corresponds to a vortex mode, see what happens. This is especially useful for a scalar vortex because we know that at the design wavelength, when you're looking exactly at 775 or whatever you're looking at, they all perform exactly the same. It's only when you start to step away that you're getting different behavior from what you expected because of this chromatic way that you're building this mask. So this is a very simple example of these three that we're comparing at the design wavelength. They've all got mode 6 because they're charge 6, so they perform exactly like you would expect. The second you start to step away from that central wavelength, so now you've got 1% and 10% wavelength offsets, you start to see all these other modes appear. And you see modes that are not even just even integer modes. You even see odd modes. That means you're getting performance corresponding to a charge 3 or a charge 1 or a charge 5 vortex. And we already know that those vortexes do not result in perfect starlight rejection. That's a big limitation to the performance that we're seeing, for example, with a regular classic vortex compared to a sawtooth. So we didn't expect to see that much of a difference when you take 0 to 12 pi versus 0 to 2 pi 6 times. But this really highlighted that, oh, that's where we're going to see all their sensitivities pop up and all these other bad factors that we want to avoid. And if it's no different to us, we might as well make it 0 to 2 pi 6 times. But the other thing that I wanted to point your attention to here, besides those odd modes, which we know are bad, is the 0th order mode. So if we have charge 6 and charge 12 is fine if we get a mode there because that's more of the same. It's not increasing the sensitivities. You're not necessarily helping the inner working angle, but you're not hurting it. But when you get a mode at 0, that's 0th order leakage. That means light passes straight through your vortex and doesn't pick up any of their phase ramp. That means you're getting stellar light that's just not even being affected. And that's really bad. That's the biggest offender here. And you only see that when you're off the central wavelength. So it starts to pop up at 1% and gets worse at 10%, 20%. So now we've come up with a way to sort of look at different designs and see a little bit more about how they're behaving without just doing regular 2D wavefront propagation. Yeah. Not really. Yeah, so that was one thing I thought was weird, that, oh, the central wavelength is actually starting to shift, but it makes sense that if you're now taking a wavelength that's off-center and it's close enough to another possible integer number of wraps, then that might be the one that it's seeing an integer number of pi phase wrap, or 2 pi phase wraps. So that might be the one that becomes a dominant mode, especially if you've just got a regular plain simple ramp. That's more likely than if you had it going back and wrapping. Yeah. Okay. So we thought, okay, the first thing was, all right, well, let's just take that 0th order mode, let's bop it down, let's see what we get, let's inverse this process and try to get a new profile out that's not so nice and simple. And this, we call this the whack-a-mole method because we were like whacking the 0th order mode, whacking all the odd modes. We were trying to get rid of all the modes we didn't like. And in the end, we were getting some profiles, but they were kind of complicated. We weren't sure if it was fabricable. We weren't really sure if it was exactly along the lines that we wanted. Even if we were to impose some constraints about like, oh, we need jumps that are exactly, 1 pi or 2 pi jumps, or we need smooth, flat lines, it was starting to get complicated and not really that insightful. And so we thought, okay, well, let's try another approach to really tackling this zeroth order leakage. And that study sort of brought us back to, this is just re-emphasizing that we noticed this difference between a regular classic vortex and the sawtooth that we had just spoken about, which is these other odd modes. And so now we're focusing on this zeroth order leakage, and that brought us to the idea of how can we better design masks that are going to still have this vortex property, not introduce any of these other bad modes, but directly combat this zeroth order mode. We know other techniques in this field. There have been other coronagraphic techniques to directly cut at that zeroth order light that's going straight through. And these are two from some papers that were before the vortex was even come up with. And so, for example, the Rade and Rade paper from 1997 and the Remy Sumer paper from 2003 came up with ways that you can put central features that are radial. So no longer are we looking at azimuthal features. So this type of work won't show up in the modal decomposition if we try to add these to the designs. But we can combine them and complement them with sort of the knowledge that we learned from the modal decomposition with some of these features. So now we're combining radial and azimuthal features. And these were two that we looked into. And I simulated each of them, and I tried to optimize, what are some of the best parameters, because these were created before the vortex was even designed, as I had just said. So the first one is a simple central dimple. It has a very specific size. It's exactly pi phase shift, so you know what it's doing. It's just equaling the flux outside of it and inside of it and making it opposite. So it's canceling that out. The dual zone, slightly more complicated. It was originally designed for apodized people, so it wasn't really made for this purpose. Much broader broadband light, 40% was the original target for that paper. So slightly different use case, but let's just see what happens when I combine these with the vortex designs that we were looking at. And so that's exactly what I did, simulating adding these to the sawtooth pattern, which we've already seen is better than the regular 0 to 12 pi ramp. And these are some of the simulated, these are all in simulation results, and this is what we call the V curve. So I call it the V curve just because you can see the shape here, and ultimately the goal is to push down the V curve, especially at the edges when you're going further and further away from the central design wavelength. You can right away see in the left plot that the purple and blue lines without any sort of radial feature, at least an order of magnitude, basically two, because if you look at the axis here, it's only labeled in increments of 100. It's so much better when you add the radial feature. Depending on which bandwidth you're looking at, you get a factor of like 78 versus 200. So it's really a huge improvement here. The idea is to see if maybe we just tried this at first with the size for the radial features that were reported in the original papers, and they weren't optimized at all with the vortex. So the next thing to do is do a big sweep, do a 2D scan of, okay, what if we change the phase offset a little bit? What if we change the size of the dimple a little bit? It's a pretty simple concept. And we found a much bigger region that might be optimal depending on the bandwidth that you're looking at. You might find yourself looking at a slightly different optimal radius for this central feature. And so now the idea is to really make one of these, combine these two things, get it made simply out of glass, simple materials, see what happens, stick it on a test bed, see if you really get that 2 order of magnitude improvement, and then work forward from there. This is already a pretty big step, I would say, in improvement compared to what we've previously tested, but we got to go in increments. If we try to go for the perfect design that's already reaching 10 to the minus 10, we're going to be stuck in simulation land for a long time. And so that was one of the nice things about this, was it's sort of definitive step in the right direction, I would say. And so just before I go over these points, this figure in the middle shows 3 different possible implementations of adding a radial central dimple like the one I just showed. But there's many different ways you can do it, because it ultimately results in a phase pattern that's just a twisted central region. So you can make one that's all in the same plane. That's much easier to manufacture. Or you can put the dimple on the backside, or you can make the dimple protruding. And the reason that that's the versatile approach is because later down the line we might be trying more and more complicated designs, and so it's nice to know that it's not that complicated to add this type of small feature for now, and we can move forward from there. So some of the major takeaways and summary points that I wanted to leave you with are that we already know that vector vortexes have a lot of potential. It's not the best necessarily, coronagraph for every application, but scalar vortexes might be a way to go if we're trying to look at not being limited by polarization sensitivity, and it's just sort of starting. People haven't really been looking at many different types of scalar designs a lot lately. And so if we really push the boundaries here, we could land on something that might even perform better. It was also interesting to look at some wavefront control methods and how those pair differently with vector versus scalar. In the end, there was a lot learned about them in terms of convergence rates, but not that much that we saw was different between the two. That's, I think, a good result, not a non-result. We saw that adding these central features already improves our contrast by 10 to the minus 2. That's a lot when we're trying to make these jumps down to 10 to the minus 10. Every little bit counts, and I would consider that to be a lot bit, not a little bit. And the next step, of course, is to make one, so that's what we're in the process of doing now. I think we're getting close to ordering one of these, and then also trying to look at different manufacturing techniques to do in-house so that we can iterate on this process a lot faster rather than like taking a long time to come up with the design, ordering it, waiting months for it, only to order another one once we characterize it and know what's good or bad about it. And then the last point, which I think is the most exciting part of this research, is that throughout all of this study, there was a lot of looking down other corridors for possible solutions and other possible ways to implement still scalar vortexes, but combat these not just with central dimples. It was definitely not the first idea that we tried, and we saw some potential in other avenues, including metamaterials. So we know that these are starting to grow in our field of astronomy and instrumentation. But simulations that I have done, that my colleagues have done, have already shown that there's quite a lot of potential to achieve more than 2 orders of magnitude with not that much difficulty. So I really think that coming up with these designs and then knowing to transfer them to other implementations, like using metasurfaces, like using multiple layers, for example, might be something that might hold the key to reaching down to that contrast level. And so the last one here is combining multiple materials. We've also done some preliminary simulations with that. If you really are smart about your material choice and the dispersion properties that are between those two, you can also gain an order of magnitude, probably more, based on my early simulations. So knowing which patterns you sort of want and then how to implement them, I think that's something that can really lead to something cool. So yeah, thank you so much for your attention. I was really happy to talk about this, and I'm happy to take any questions. Yeah. I can just give you the mic. It's not on a...
So I'm curious, do you have a sense for like what's the best performance you can get with any phase mask? Do you have a sense for like, I mean, you're really trying to achromatize these vortex masks, but like what is the theoretical limit? Like if you, how well can you actually do? Are you close to that? Like if you, suppose you just allowed the radial and azimuthal parameters to vary freely and you had a 2D grid, and what is the best possible phase mask that you can possibly get, and how well do these compare to that?
Thanks for being my mic runner. Yeah, okay, this is a totally good question, and I think I have to separate two different types of answers that I would immediately come to, which is one, in simulation world, where everything is just perfect and I'm not simulating any aberrations or errors or anything like that. The math for a perfect vortex, right, not even in simulation, like just on paper, shows perfect solid rejection. But that doesn't mean that that's not going to be the thing we're limited by. Because when we take it into the lab and we look at contrast budgets, like the ones that the HCIT folks presented, there's a lot of other things that are limiting us that are not the mask. But now, if we are looking just at the mask, I know that people have done this like free parameter, whatever the optimizer sort of lands on solution for apodizers, I think. I'm not sure if somebody else here in the room is more familiar with that than I am. But I haven't looked that far away from the general vortex principles, because we know that there are some favorable properties that we don't want to lose for this particular application, including, and I didn't show any here, but in my recent paper and one that's coming out soon, I do all the simulations for sensitivities to aberrations, and those go kind of crazy the second you sort of step away from a lot of these favorable features. a vortex mask. So I don't have an answer for you that you might want to hear, but I can tell you why I haven't looked into the totally free problem completely. Yeah. Right. So actually, you should definitely talk to Lorenzo after this if you're interested, because we have done a lot of recent work where we got a much flatter performance with metasurfaces. It's barely the V shape, and it goes down 2 orders of magnitude, but it's starting to plateau in terms of how much farther we can go down. And so if you're looking for not a V curve, we've already got one of those. We've got many of those. If you're looking for a W curve, we've got those. You know, there's a lot of possibilities to move away from this shape of performance. It's a lot more achromatic, but we're not just looking for achromatic. So that's why. But yeah, I think he has a lot of results that you can ask about that we've been working on. And also Scalar Vortex, who's a graduate student from Santa Barbara, he's also working on metasurfaces with us, and has been starting some lab manufacturing and testing of some of those as well. And so there's some answers for you maybe in those recent papers.
That was an awesome talk. Thank you. I have a question about the figures in the center. What sort of manufacturing tolerances do you have on those vortex shapes, especially in the dimple? Because depending on your dimple size, just getting a dimple is really challenging, especially, I mean, even with classical lithography techniques or anything. So what sort of manufacturing tolerances do you have on those?
Yeah, it's a good question, and I'm just sort of myself moving into the understanding manufacturing a little bit more, because it's not what I've been doing. But my discussions so far with our vendor Zeiss, who made the last ones, for sure have been centered around the central defect being really small, and they're able to meet and exceed our expectations for the central defect size. So I think on the last one, you can check my paper, or I can tell you after this, was I want to say between 11 and 18 microns was the size of central defect, and they're able to do even better than that. But we looked at the F number of our test bed, which at the time was 32, and now it's 85. So it's improved a lot. We've redesigned our test bed, but still, it's good enough for that. Another thing that we looked at was the discrete steps, not along the staircase, but instead along the edges. They also have still some sort of discrete process for making these supposedly smooth lines. And so I was able to measure that myself when I got them. And it didn't seem to be a problem for us, but it is an issue when you're going to put one of these on sky, because you don't want a planet to fall right where that sector is. And so you don't want that gap to be really huge. And so you want your wall to be as straight as possible and not sort of angled or slanted. And I have some tolerances that we've written down for percentage of how far off from flat or straight we need. And so I can show you afterwards, because I don't have them off the top of my head. But one of the things that I think I learned from these discussions with the vendors was between these 3 designs, the middle one is the simplest because it's all in one plane. So when you're doing regular photography, you can sort of just say that this is a pattern that we want, and they seem very optimistic. And the ones we got from them before, we had ordered one simple design. They gave us 13. They were super reliably made. I characterized them all myself. They were incredibly consistent between them. And they performed well in the test bed. We didn't have any problems with the air coating was spectacular. I'm worried that if we try to make these ourselves, it's going to be a big issue that we're going to run into. So yeah.
So I was curious about a couple of things. First one is, particularly with the tolerance questions on these sawtooth things, you've effectively added diffractive elements into your focal plane mask. But I didn't know, it looked like you were showing some optimizations of the coronagraph itself. Was there any consideration for whether or not any one of these particular mask implementations is making the wavefront control more difficult?
Yeah, so I didn't show any single one of the dark holes that I simulated because I did always try to take every possible design that I was considering and showing V-curves for to also do wavefront control with them. And there were a couple of places where I would reach some hiccups where I was like, well, it's weird that, EFC won't converge here. Maybe it's trying to correct for two exactly opposite patterns that it's seeing, and it's not able to sort of come with a better solution. And the radiate dimple is one of the things, this central dimple, is one of the things that we're a little bit worried about if it is going to, because simulations show you get improvement with wavefront control, but not as much as I would have expected or wanted. And so we need to figure out what's going on there. And the more I simulate it, the more I'm confused. So I really want to put one in a test bed and see if we try different methods, and I haven't simulated any other wavefront control method yet other than regular pairized probing EFC with this. But I don't think that, for example, going from a staircase to smooth sawtooth has shown a difference, because I've seen that in simulation when you do regular wavefront control without the dimple, you see pretty good improvement, and it's not noticeable how much of a difference those two make between each other. In terms of that one question, it was something I was worried about, like getting more total internal reflections if you go from nice discrete step heights to grayscale, like nice smooth ramps. But I don't think I have anything to worry about because of those simulations. But maybe I'll see you a few months from now, and I'll be singing a different tune. Hopefully not. Yeah.
Great talk, Niyati. Really cool results. We are working now on trying to understand the yield for spectroscopy, not just for broadband photometry and detection for different designs. So the key factor for us in that is understanding the contrast variation as a function of distance from the central or optimal wavelength. And I can assume, you showed average contrast for different wavefront control strategies. Are you able to produce contrast? I'm sure you are. It would be really valuable for us to be able to understand that variation in, say, factor of contrast, degradation, and shape. Because if you're doing, equally well at long wavelengths, but you drop off terribly at short wavelengths, that affects what your optimal bandpass is and how effective that would be. So it'd be great if you either could show that or provide that or whatever to the community. That'd be helpful.
Yeah, just to clarify, you're talking about with like dark hole digging, right? Yeah. So I definitely have all of that data because we save it all in subbands. So I could easily produce a V-curve for you for different, like with wavelength as the x-axis and the contrast still as the y-axis. Easily could definitely do that, and it could be interesting to see how it changes. And I also just for, I think a couple of times I just randomly was trying to see if I moved what bandpass I cared about away from what not centered on the central wavelength that I've designed for, because I was having some problems with wavefront control, and like maybe it was trying to optimize the two different ends of the bandpass exactly with opposite solutions. So I tried doing stuff like that. It's really easy to sort of get some diagnostics about this because of the way that the simulations run and the experiments. It's all so I'm happy to sort of follow up with you about that if you're interested.
I have another tolerancing question. Do you have any sense for how sensitive the scalar designs are to the alignment of the mask with respect to the beam orientation? Because when you have, and Tyler's question made me think of this, when you have, for example, the sawtooth or the staircase, you're looking at that just maybe not normal to the beam, but a little bit off. Now you're seeing a very strong discontinuity in the mask if you're looking at it from an angle, right? So you have to make sure that those aligned very, I would imagine, very precisely in the beam. And I'm just wondering if you have any sense of how tight the alignment tolerance is and how it varies with design.
Yeah, so I think the question that you're asking is really related to tilt sensitivities, and so I definitely have done those plots, and I haven't seen that it's something that we could restore by adding, for example, the dimple. So that was one thing that we saw. So let me backtrack for a second. When I compare a regular vortex with a scalar vortex with all of these like discrete lines and these sector jumps, we do get a little bit of a hit on the tip tilt. And I think I've put one of those plots in one of my papers, but if not, I definitely have it easy to access. Okay. Yeah, I think. So you're not talking about the case where the light is coming in exactly normal to the mask, but it's just offset. That's right, 'cause that would be. Yeah. Okay. Yeah. Yeah. I have to think about. I don't think it would be that hard to simulate that though, but I haven't done it yet. Is the answer to your question? And I'm trying to think about now when we went to go install this mask the very first time on each of these test beds, whether we had any extra difficulties with that. Mhm. Yeah, I see what you mean. Yeah, definitely.
Yeah. No, have you considered, so all this is charge 6 Vortex, but if it were to be charged for maybe with the dimple, manufacturing would be much easier in terms of adding the dimple and things like that, because, you're reducing basically the phase change in a small region. Have you considered, or is there a plan to try different charges of Vortex to do this type of studies?
Yes, I haven't because I've just been trying to do a nice comparison, but I don't see any reason to believe that you wouldn't be able to translate some of the things that we've learned about adding a central dimple to a vortex there, especially things like doing the modal decomposition on charge 4. I've done that many times and it looked exactly as expected, and you have less possibilities for other bad modes because but again, we did charge 6 because of the reason that, even though you're taking a hit out in a working angle, you get the extra sensitivity. So then if you're moving down to charge 4, you even have more sensitivity. So it's just something to think about, but I don't see any reason to see that it would be limited there, and could easily. There was actually, for a while, I was doing all of these in 6 and 8, and the reason I went to 8 was because there have been some ideas to not just do perfect vortex, but some weird phase wrapping where you have 3 pi jumps and 5 pi jumps by the Paris group, and they wrote one paper about it and sort of didn't continue on that path at all. And it was also because there was at least they didn't talk about it in the paper, but when I submitted, I saw a lot of sensitivity hits that you get from doing weird wrapping, and so I just stick to charge 6. Let's see what we can get from here, and then trying to make every lesson that we learn transferable. But it's a good point. Yeah.
So just a comment related to what Scott was asking. You can do all the diffractive modeling that you want. I think one of the practical issues with the angle of incidence on the focal plane mask is going to actually be a normal optics thing, which is glint. It'll take very little glint of the core to affect you at very high contrast levels, and that'll probably result in an incoherent background you'll observe. Because you can error code it all you want. If you hit that at 80 degrees angle of incidence, I guarantee you it's 100% reflective. But then my question though was, so you're using fused silica? Okay. I was curious why you chose the wavelength range that you did, because in terms of scalar phase offsets and index of refraction, 700 nanometers is about the worst wavelength you could choose for using fused silica and keeping constant index. So is there a driver for that? Why not go to a friendly spot?
It's really because source that's centered around there. We know we have Gaussian tunable filters around there, so it's built totally, and it was built with the F number of that testbed in mind, with the wavelength range that we know we have sources for, as well as the JPL testbed has the same sort of range. So the new ones that we're going to get made are almost the same. It's like 760, because that's what we have the facility to test and characterize in. Yeah. But yeah, do you think? Yeah. I mean, so this is really good to talk about material choices, and it's really outside of what I am knowledgeable about right now, but I'm trying to get to know more, because we're looking at other possible things for, especially these dual layer things. So we're looking at like materials, and you can tell me if you think this is crazy, because I wouldn't really know as much, but from what we've been discussing with vendors and manufacturers, things like silicon nitride and titanium oxide make a good combination. Zinc selenide, which is a really hard material to work with, works really well. You get 2-3 orders of magnitude improvement when you're able to combine these together. You get 10 to the minus 11 easily. So it's like, I really want that, but we're trying to work with places that can give us what we need. So, but the two that you had said were calcium chloride and barium. Good to know. Yeah. But really. Yeah, I think also what you end up looking at with that is then the thickness has to be something still reasonable. So, I mean, yeah. So that was something we would like we'd find an element that we really like and be like, this is a great material choice, combine it with this, but then it becomes like hundreds of microns thick. You can't really get that very easily, and so these are the concerns we're looking at. But I'll look into the ones that you had mentioned.
Well, I think the time is up. Thank you so much for the talk, and thanks for the questions. We're gonna